Imagine a world where catastrophic tides surge across continents, where nights descend into absolute darkness, where ice ages far more severe than any Earth has witnessed grip the planet for millennia, and where evening skies glow with shades of tungsten and amber never before seen by human eyes. This is the reality that awaits if we were to replace our moon with other celestial companions from across the solar system. The consequences would be extraordinary, transformative, and in most scenarios, utterly devastating to life as we know it. Titan, the hazy giant. Our journey begins with Titan, Saturn's largest moon and one of the most enigmatic bodies in our cosmic neighborhood. For billions of years, humanity has gazed upon the familiar face of our moon, its surface draped in gray lunar regolith, its silvery light painting landscapes in monochrome beauty. But what if that familiar sight were replaced by something entirely different? What if, when you looked up at the night sky, you saw Titan hanging there instead? Titan represents a celestial paradox. As the second largest moon in the entire solar system, this behemoth exceeds even Mercury in diameter, making it larger than the smallest planet in our stellar family. Yet despite its impressive size, Titan remains trapped in the frigid outer reaches of our solar system, where temperatures plummet to a bone-chilling -180 degrees Celsius, equivalent to -290 degrees Fahrenheit. At these extreme temperatures, the familiar rules of terrestrial chemistry transform into something alien and wondrous. The surface of Titan bears an uncanny resemblance to Earth in its geological features. Rivers carve through ancient terrain, lakes dot the landscape, and vast seas stretch across substantial portions of its surface. But these are not bodies of water as we understand them. Instead, liquid methane and ethane flow through Titan's hydrological cycle, creating a world that mirrors Earth's geography while remaining fundamentally alien in composition. Swimming in these methane seas would be inadvisable, to say the least. If we were to swap our moon for Titan, the transformation of Earth's night sky would be immediate and dramatic. Gone would be the silvery white lunar glow that has illuminated human civilization since our species first looked upward in wonder. In its place, a golden-orange twilight would suffuse our nights, casting landscapes in warm, almost sunset-like hues, even in the depths of midnight. This new celestial companion would loom approximately 1.5 times larger than our current moon in apparent diameter, creating a presence both magnificent and slightly unsettling in its enormity. But Titan's most distinctive feature lies in its atmosphere, a characteristic that makes it virtually unique among moons in our solar system. A thick, nitrogen-rich envelope surrounds this world, extending nearly 600 kilometers into space. This atmospheric blanket, denser than that of any other moon and more substantial than many planets, would give Titan the appearance of a giant fuzzy orange orb suspended in our sky. The diffusion of light through this dense atmosphere would create a soft, almost ethereal glow, fundamentally different from the sharp-edged lunar disk we currently observe. For astronomers and casual stargazers alike, this transformation might seem merely aesthetic, perhaps even beautiful. But the consequences would extend far beyond visual appeal. Titan possesses approximately 80% more mass than our moon, and this additional gravitational pull would have profound implications for Earth's oceans. The delicate gravitational dance between Earth and moon, refined over 4.5 billion years of orbital mechanics, would suddenly shift to a new and more violent rhythm. Tides on Earth would undergo a dramatic transformation. High tides would surge far beyond current levels, while low tides would retreat to unprecedented depths. Coastal cities worldwide, home to billions of people and representing trillions of dollars in infrastructure, would face inundation twice daily as tidal forces dramatically stronger than those we currently experience drove seawater far inland. Ancient port cities that have stood for millennia would find themselves underwater during high tide, their streets transformed into canals, their foundations undermined by relentless erosion. The erosion itself would accelerate catastrophically. Coastlines that have remained relatively stable throughout recorded human history would begin to reshape themselves at geological speeds visible within human lifetimes. turbulence along every coast would increase dramatically as the enhanced tidal forces stirred ocean waters with unprecedented vigor. Beach erosion, already a concern in our current configuration, would become a crisis of existential proportions for coastal communities. Properties that have commanded premium prices for their oceanfront views would literally disappear into the sea, claimed by tidal forces beyond human ability to resist or control. Meanwhile, Titan itself would undergo equally dramatic changes. For billions of years, this moon has existed in the cold, dim outer solar system, where sunlight arrives weakened and distant, providing only a fraction of the energy that bathes the inner planets. But transplanted to Earth's orbit, Titan would suddenly find itself flooded with solar radiation orders of magnitude, more intense than anything it has experienced in its long existence. The consequences of this increased energy input would be transformative and irreversible. The methane lakes that dot Titan's surface, stable for eons in the deep freeze of the outer solar system, would begin to evaporate. What has been liquid would become gas, creating a thick, methane-rich atmosphere that would dwarf the moon's current atmospheric envelope. As temperatures continued to rise, the icy crust that has remained solid throughout Titan's history would begin to succumb to the unaccustomed warmth. Melting would begin slowly at first, then accelerate as feedback mechanisms amplified the warming process. Beneath Titan's icy shell lies one of the solar system's great mysteries, a subsurface ocean of liquid water that may extend hundreds of kilometers deep into the moon's interior. As the ice melted away, this hidden ocean would be revealed to direct observation for the first time in history. The scientific implications would be staggering. If life exists anywhere beyond Earth, Titan's subsurface ocean represents one of the most promising candidates for harboring it. With the moon suddenly accessible in Earth's orbit, just 3 days away rather than nearly 1 billion kilometers distant, humanity could explore this alien ocean firsthand, searching for signs of biology in an environment that has remained isolated from the rest of the solar system since the dawn of planetary formation. But this window of opportunity would be tragically brief. Titan's low gravity, sufficient to retain its atmosphere in the cold outer solar system, would prove inadequate in the warm inner solar system. Over millions of years, the moon would gradually lose its atmospheric gases and its newly exposed ocean to space. Solar wind and thermal escape would strip away the volatiles that make Titan unique, transforming it into an airless, waterless husk. The hazy methane orb that replaced our moon would eventually become as barren and lifeless as the gray sphere it displaced, a cosmic tragedy played out over geological timescales, but inevitable from the moment of the swap. Ganymede, the magnetic marvel. If Titan seems imposingly large, Ganymede takes celestial magnitude to another level entirely. This Jovian moon holds the distinction of being the largest moon in the solar system, exceeding even Titan in diameter and mass. Ganymede possesses another unique characteristic that sets it apart from every other moon in our cosmic neighborhood: its own intrinsic magnetic field, generated by dynamo processes in its metallic core, making it the only moon known to possess this planetary characteristic. At approximately 1.5 times the diameter of our moon, Ganymede would appear roughly similar in size to Titan when viewed from Earth's surface. But while Titan casts a golden-orange glow, Ganymede would shine with brilliant intensity. The moon's surface consists largely of water ice, and this highly reflective coating bounces far more sunlight back toward Earth than our moon's darker regolith. The result would be nights dramatically brighter than those we currently experience, with Ganymede flooding the landscape with reflected solar radiation. For professional astronomers, this increased brightness would present serious challenges. Deep space observation depends on dark skies, free from light pollution and excessive background illumination. With Ganymede overwhelming the night sky with its brilliance, telescope observations would become significantly more difficult. Faint galaxies and distant quasars that currently lie at the edge of detectability would disappear entirely, washed out by the glare of our new lunar companion. Amateur stargazers would face similar frustrations, as the enhanced moonlight drowned out all but the brightest stars and planets. For ordinary citizens, the impact would be more prosaic, but no less significant. Bedroom curtains adequate for blocking normal moonlight would prove woefully insufficient against Ganymede's illumination. Sleep disruption would become a widespread problem, potentially affecting public health on a global scale. Blackout curtains would transform from luxury items to necessities, and even these might prove inadequate in some circumstances. The subtle rhythms of the lunar cycle, ingrained in human biology through millions of years of evolution, would be replaced by something altogether more intrusive. Yet these inconveniences pale in comparison to the gravitational catastrophe that Ganymede's mass would unleash. At approximately twice the mass of our moon, this giant satellite would exert gravitational forces that would literally reshape Earth's oceans and even its solid crust. The term megatides scarcely captures the scale of the phenomenon. Tidal ranges would increase to levels unprecedented in Earth's history, dwarfing even the extreme tides seen in places like the Bay of Fundy or the Severn estuary. Coastal flooding would occur twice daily with clockwork regularity, as the enhanced tidal forces drove seawater far beyond current high tide marks. Cities built at elevations that have been safe throughout human history would find themselves submerged. Infrastructure, designed with generous safety margins for tidal variation, would be overwhelmed. The economic and human costs would be incalculable, as coastal zones representing the most densely populated and economically productive regions of the planet became uninhabitable. Wave activity would intensify proportionally. Storm surges, already among the most destructive natural phenomena, would reach apocalyptic levels when combined with these enhanced tides. Hurricane storm surges that currently push water several meters above normal sea level would drive walls of water tens of meters high across coastal landscapes. The erosion caused by these relentless tidal forces would reshape coastlines within decades rather than millennia, as nature rapidly adjusted to the new gravitational reality. But Ganymede's influence would extend beyond the oceans. Earth's crust itself would feel the gravitational squeeze. Just as Jupiter's gravity kneads Io into a volcanic hellscape, Ganymede's enhanced gravitational field would flex Earth's crust in ways it has not experienced since the early bombardment period billions of years ago. This crustal deformation would trigger earthquakes along fault lines worldwide, as tectonic stresses exceeded the strength of rock. Volcanic systems, particularly those already in delicate equilibrium, would be pushed into eruption by the added stress. Paradoxically, amid this catalog of catastrophes, Ganymede would bring one significant benefit to Earth. The Moon's massive gravitational presence would act to stabilize Earth's axial tilt with even greater effectiveness than our current Moon. Earth's axis currently maintains a relatively stable angle of approximately 23.5 degrees, providing us with regular seasonal cycles and preventing the extreme climate variations that would result from a wildly wobbling axis. Ganymede would lock this tilt even more firmly, preventing the slow oscillations that currently occur over tens of thousands of years. This enhanced stability would effectively eliminate ice ages from Earth's climatic future. The advance and retreat of glaciers that has characterized the past several million years of Earth's history results partly from subtle variations in Earth's orbital parameters and axial tilt. With Ganymede providing a more powerful stabilizing influence, these variations would be suppressed, and Earth's climate would settle into a steady state. For a civilization concerned about climate stability, this represents a genuinely positive outcome, assuming, of course, that any civilization survives the initial catastrophes of the swap. Ganymede itself would undergo profound changes in Earth's orbit. Throughout its existence orbiting Jupiter, Ganymede has dwelt in perpetual twilight, receiving only a small fraction of the solar energy that reaches Earth's orbit. At Jupiter's distance from the Sun, solar intensity drops to roughly 1/30th of what we experience on Earth. On its warmest days, Ganymede's sun-facing surface reaches a relatively balmy -112 degrees Celsius, which would feel positively tropical compared to its nighttime temperatures. Transplanted to Earth's orbit, Ganymede would be bathed in solar radiation more than 30 times more intense than anything in its previous experience. The moon's massive ice crust, approximately 150 kilometers thick and stable for billions of years, would begin to sublime and melt. Water ice would transition directly from solid to vapor in the vacuum of space, or where conditions permitted, melt into liquid. The transformation would be gradual at first, but would accelerate as the process continued. Beneath that thick ice shell lies one of the solar system's most voluminous oceans. Scientists estimate this subsurface sea extends to depths of 100 kilometers or more, making it far deeper than any terrestrial ocean. As the ice melted away, this ocean would be exposed to direct sunlight for the first time in its existence. Clouds would form over the new seas. A water cycle would establish itself. Ganymede would transition from an ice-locked moon to a genuine water world, sporting oceans that would dwarf Earth's in depth, if not in surface area. The scientific and exploratory opportunities would be extraordinary. A water-covered moon, possessing its own magnetic field and potentially harboring life in its long-hidden ocean. Located just 3 days away by spacecraft, this would represent a revolution in planetary science and astrobiology. Research stations could be established on whatever landmasses remained above the new seas. Submarines could explore the alien ocean depths, searching for ecosystems that evolved in isolation since the solar system's formation. Ganymede's magnetic field would create another spectacular phenomenon visible from Earth. The moon already generates auroras where charged particles from the solar wind interact with its magnetic envelope. Transplanted to Earth's orbit, these auroras would become far more intense and visible. Observers on Earth would have the extraordinary experience of watching northern lights on 2 separate worlds, simultaneously Earth's familiar auroral displays, and Ganymede's cosmic light show playing out across an alien sky. The scientific value of studying a magnetosphere so close at hand would be immense, providing insights into planetary magnetic fields that could reshape our understanding of how these protective shields form and evolve. Io, the volcanic inferno. Among Jupiter's extensive family of moons, one stands out for its geological violence. Io, the third largest Jovian satellite, holds the distinction of being the most volcanically active body in the known solar system. Hundreds of active volcanoes dot its surface, continuously erupting fountains of molten sulfur lava hundreds of kilometers into space. The mechanism driving this extraordinary volcanism differs fundamentally from that of Earth. Where terrestrial volcanoes draw their energy from radioactive decay in Earth's interior and residual heat from the planet's formation, Io's inferno is powered by relentless gravitational forces. Io exists in a gravitational vice. Jupiter's immense mass pulls from one direction while the substantial moons Europa and Ganymede exert their own gravitational influence. As Io orbits, these competing forces flex the moon's interior, generating friction and tremendous heat through a process called tidal heating. The moon's interior literally melts under this gravitational kneading, and the molten material finds release through countless volcanic vents. Molten sulfur lakes glow across the surface. Plumes of volcanic material arc into space. The entire moon constantly reshapes itself through volcanic activity that makes Earth's most active volcanoes seem gentle by comparison. Swapping our moon for Io would create a spectacle unprecedented in human experience. From Earth, Io would shine approximately 5 times brighter than our current moon, its surface glowing with a golden-orange radiance created by sulfur compounds and reflected sunlight. The visual impact would be stunning, but the true magic would be revealed through even modest telescopes. Amateur astronomers could watch volcanic eruptions occurring in real time on the lunar surface, observing fountains of molten material being blasted into space by explosive volcanic forces. The sight would be simultaneously beautiful and terrifying, a constant reminder that our new lunar companion was a world of unimaginable violence. Where the surface temperature fluctuates wildly, depending on proximity to active lava flows, and where standing in the wrong location would mean instant death from volcanic bombardment or toxic fumes. This hellish world, suspended in our sky, would fundamentally change humanity's relationship with its satellite. No longer would the moon seem like a potential destination for colonies and expansion. Instead, it would appear as a cosmic warning about the destructive power that gravitational forces can unleash. But appearances can be deceiving. Despite Io's fearsome reputation and spectacular volcanism, swapping it for our moon would actually have relatively benign consequences for Earth. The key lies in Io's physical characteristics. This moon possesses remarkably similar size and mass to our current moon. While not identical, the differences are small enough that the gravitational effects on Earth would be minimal. Tides might increase slightly, but nothing approaching the catastrophic megatides that Ganymede or Triton would generate. The truly fascinating transformation would occur not on Earth, but on Io itself. The volcanic violence that defines this moon results entirely from the gravitational stress imposed by Jupiter, Europa, and Ganymede. Remove Io from that gravitational vice, and the fundamental energy source driving its volcanism disappears. Transplanted to Earth's orbit, Io would suddenly find itself in a gravitationally calm environment. No massive planet looms overhead, flexing its interior with every orbit. No competing moons tug from different directions, ensuring that the stress never relents. Without this constant gravitational kneading, Io's volcanism would begin to wind down. The most active volcanoes would fall silent first, their immediate magma sources exhausted without tidal heating to replenish them. Over time, as the moon's interior cooled, volcanic activity would diminish steadily. Lava lakes would solidify, eruption plumes would cease. Within a relatively brief period, geologically speaking, Io would transition from the most volcanically active body in the solar system to a quiet, dormant world. The long-term fate of Io would be to become cold and geologically dead, not unlike our current moon. Billions of years ago, our moon likely experienced its own period of volcanic activity, when radioactive decay and residual formation heat kept its interior molten. But these energy sources eventually depleted, and for roughly the past 3 billion years, the moon has been essentially geologically inactive. Io would follow a similar trajectory, its spectacular volcanism proving to be temporary once removed from Jupiter's gravitational influence. Future generations would look up at a gray, crater-marked sphere, scarcely distinguishable from the moon it replaced. With only historical records and possibly visible lava flows frozen in time to suggest the inferno that once raged across its surface. Europa, the ice, crusted ocean world. Few moons have captured scientific and public imagination quite like Europa. Since the Voyager spacecraft first flew past Jupiter and its retinue of moons in 1979, Europa has represented one of the most compelling targets in the search for extraterrestrial life. The moon's icy crust, relatively young by geological standards and marked by complex patterns of cracks and ridges, suggested something remarkable might lie beneath. That initial intrigue has only deepened with subsequent observations and theoretical work. The Galileo spacecraft, which orbited Jupiter throughout the 1992 and early 2000s, made a puzzling discovery while mapping Jupiter's magnetic field. In the region where Europa orbits, the magnetic field showed unexpected distortions. Europa lacks an intrinsic magnetic field like Ganymede's, so what could be causing this disruption? The answer, scientists believe, lies hidden beneath the moon's icy shell. Europa likely harbors a vast subsurface ocean of liquid water, possibly extending to depths of 150 kilometers. This ocean has remained liquid for billions of years, despite the intense cold of the outer solar system, kept warm by tidal heating similar to that which drives Io's volcanism, though far less intense. As Jupiter's magnetic field sweeps across Europa during the moon's orbit, it induces electrical currents in the subsurface ocean, much as a magnet moving past a conductor generates electricity. These currents create a secondary magnetic field that distorts Jupiter's primary field in exactly the way that Galileo observed. This indirect detection of Europa's ocean represents one of the great triumphs of planetary science. Without ever drilling through the ice or deploying submarines, scientists have found compelling evidence for one of the largest bodies of liquid water in the solar system. The astrobiological implications are profound. On Earth, wherever liquid water exists, life exists. From the deepest ocean trenches to underground aquifers kilometers beneath the surface, life has found ways to exploit every available aquatic niche. If the same principle applies elsewhere in the solar system, Europa's vast ocean represents one of the most promising habitats for extraterrestrial life. Swapping our moon for Europa would dramatically alter both worlds. From Earth's perspective, the most immediate change would be visual. Europa's icy surface ranks among the most reflective in the solar system, bouncing back more than 5 times as much light as our moon's darker regolith. Nights would become significantly brighter, though not quite to the extent that Ganymede would produce. The enhanced brightness would again challenge astronomers and stargazers, though the effect would be less extreme than with larger, more massive moons. Europa's lower mass compared to our moon would have one beneficial effect: weaker tides. The tidal forces that currently shape Earth's oceans would diminish, leading to smaller tidal ranges. Coastal communities would actually benefit from this reduction, at least in the short term. The Bay of Fundy would see less dramatic tidal shifts. Tidal rivers would experience reduced flows. Maritime activities dependent on tidal patterns would need to adjust to the new, gentler rhythm. But this gravitational benefit would come with a long-term cost. Our moon plays a crucial role in stabilizing Earth's axial tilt, preventing the wild oscillations that would produce extreme climate variations. Europa, with its lower mass, would provide less stabilizing influence. Over millions of years, Earth's axis would begin to wander more than it currently does. The stable 23.5-degree tilt we enjoy would give way to variations that could push the tilt several degrees higher or lower. These tilt variations would drive climate changes far more severe than anything humanity has experienced in recorded history. When Earth's tilt increases, seasons become more extreme: hotter summers and colder winters. When the tilt decreases, seasons become more moderate, but polar regions receive less sunlight and ice sheets expand. Over geological timescales, these variations would produce climate swings that could challenge the adaptability of many species, potentially leading to waves of extinction as environments transformed faster than evolution could accommodate. Yet in the short term, swapping for Europa would provide an extraordinary scientific opportunity. Instead of being located nearly 2 billion kilometers away in the outer solar system, Europa would orbit just 385,000 kilometers from Earth, the same distance as our current moon. The moon would be accessible by spacecraft in just 3 days rather than requiring multi-year missions with complex gravity assists and massive fuel requirements. If NASA's plans to return humans to the moon by 2027 proceed, similar missions to Europa could follow within just a few additional years of development. Imagine the scientific possibilities. Landers could touch down on Europa's icy surface, studying the composition and structure of the ice in detail. Drilling rigs could bore through the ice shell, which might be as thin as a few kilometers in some locations. Submarines could be deployed into the subsurface ocean, exploring an alien aquatic environment that has remained sealed off from the rest of the solar system for billions of years. If life exists in that dark ocean, evolved in complete isolation from terrestrial biology, discovering it would represent arguably the most significant scientific finding in human history. Europa itself would undergo profound changes in Earth's orbit. The ice that has encased it for eons would begin to respond to the increased solar radiation available in the inner solar system. Tidal heating from Jupiter would cease, removed from that gravitational influence, but solar heating would more than compensate. The ice shell would begin to sublime and melt, gradually exposing the ocean beneath to direct contact with space and sunlight. As the ice melted, Europa would transition from an ice world to a water world. The frozen crust that has preserved the ocean for billions of years would give way to open seas. Water vapor would form an atmosphere, thin initially, but growing thicker as more ice melted. Clouds would form, weather patterns would develop. Europa would become a genuine ocean moon, visible from Earth as a blue-white sphere quite different from its current icy appearance. This transformation would be tragically temporary. Over millions of years, lacking Jupiter's gravitational grip and possessing only modest surface gravity, Europa would gradually lose its ocean to space. The same process that stripped Titan of its atmosphere and water would operate on Europa, though perhaps more slowly given the moon's slightly higher gravity. Eventually, the water world would dry out, becoming another airless, crater-marked body indistinguishable from countless other moons throughout the solar system. But for a brief period, cosmically speaking, humanity would have a water-covered moon to explore and study, a laboratory for understanding ocean worlds throughout the galaxy. Triton, the retrograde ice world. Neptune's largest moon, Triton, stands as one of the solar system's genuine oddities. While most large moons orbit their planets in the same direction as the planet rotates, a configuration resulting from the formation process of planetary systems, Triton does exactly the opposite. This retrograde orbit, unique among major moons, suggests a dramatic origin story. Triton likely formed elsewhere in the outer solar system, perhaps in the Kuiper Belt, and was later captured by Neptune's gravity in a close encounter that bent the moon's trajectory into its current backward orbit. If we swapped not just our moon but also its orbital direction, replacing it with Triton and its retrograde motion, we would have a moon traveling the wrong way around Earth. This backward motion would create unusual sky patterns, with Triton rising in the west and setting in the east, opposite to every other celestial object visible from Earth. The psychological impact of this reversal should not be underestimated. Countless cultural and religious traditions incorporate the moon's familiar east-to-west motion, and reversing it would feel fundamentally wrong in ways difficult to articulate. Triton's surface ranks among the most reflective in the solar system, with an icy coating that bounces back most of the sunlight that reaches it. From Earth, Triton would appear bright, though its smaller size would make it less visually impressive than giants like Ganymede or Titan. More importantly, Triton's significantly lower mass compared to our moon would result in dramatically weaker tides. The oceanic tides that currently shape coastlines and marine ecosystems would diminish substantially, with the sun becoming the primary driver of tidal forces rather than the moon. Solar tides amount to roughly half the strength of lunar tides in our current configuration. With Triton replacing the moon, overall tidal forces would drop to approximately half their current levels. For coastal communities, this represents a mixed blessing. Lower tides would mean less extreme tidal ranges, reducing erosion and making maritime activities less dependent on precise timing. But it would also fundamentally alter coastal ecosystems that have evolved over millions of years to exploit the current tidal regime. Marshlands and tidal pools, among the most productive ecosystems on Earth, depend on the regular cycle of inundation and exposure that tides provide. Marine organisms time their reproduction and feeding behaviors to tidal patterns. Reducing tidal forces would disrupt these finely tuned ecological relationships, potentially causing cascading effects through coastal food webs. Fish species that spawn in tidal zones might fail to reproduce successfully. Birds that time their feeding to low tides would find their food sources altered. The long-term ecological consequences would be complex and difficult to predict. Over millions of years, the reduced gravitational pull would allow Earth's axial tilt to wander more freely. The stable climate regime that has characterized the recent geological past would give way to more variable conditions. Ice ages would become more frequent and severe. Warm periods would potentially become warmer. The predictable progression of seasons would acquire additional layers of complexity as Earth's axial tilt oscillated through a wider range than currently occurs. But in its early days in Earth's orbit, Triton would provide spectacular displays. This is no ordinary frozen world. Triton ranks among the most geologically active bodies in the solar system, despite its small size and frigid temperatures. The secret lies in cryovolcanism, volcanic activity involving icy materials rather than molten rock. Triton's cryovolcanoes erupt fountains of nitrogen ice, water ice, and other frozen volatiles up to 8 kilometers into space, creating plumes visible from great distances. On Earth, we would have a front-row seat to these extraterrestrial ice geysers. Telescopes would reveal eruptions happening in real time as nitrogen geysers blasted material high above Triton's surface. The physical processes involved would be fundamentally different from terrestrial volcanism instead of magma rising from a molten interior. These eruptions would involve materials that are solid at Triton's current temperature, but which sublime or melt under specific conditions of pressure and temperature. Triton's surface ranks as one of the coldest places in the solar system, with temperatures reaching -235 degrees Celsius. At these temperatures, nitrogen, normally a gas at terrestrial conditions, freezes solid. Water ice becomes hard as steel. Chemical reactions that proceed rapidly at Earth temperatures slow to glacial paces. But transplanted to Earth's orbit, Triton would rapidly warm. The solar radiation intensity at Earth's orbital distance exceeds that at Neptune by a factor of roughly 1,000. Triton would be flooded with energy beyond anything in its previous experience. The frozen nitrogen that coats Triton's surface would be among the first casualties of this warming. Nitrogen ice vaporizes at relatively low temperatures compared to water ice, and as sunlight warmed Triton's surface, the nitrogen would rapidly sublime, transitioning directly from solid to gas. This vaporization would create a thick atmosphere of nitrogen, similar in composition to Earth's atmosphere, but without oxygen. The atmosphere would grow denser as more nitrogen sublimed, potentially creating a haze layer that would give Triton a fuzzy appearance reminiscent of Titan. If the warming continued long enough, Triton might develop a comet-like tail. Material subliming from the sunward side would be blown back by solar wind and radiation pressure, creating a stream of gas and particles extending away from the sunday. This tail would be visible from Earth as a faint streak extending from Triton, a constant reminder that our new moon was literally evaporating in the unaccustomed warmth of the inner solar system. Beneath Triton's icy crust, some scientists believe a subsurface ocean might exist, kept liquid by tidal heating from Neptune and radioactive decay in Triton's interior. If such an ocean exists, and the ice shell melts sufficiently, this ocean could be exposed. Triton would briefly become another ocean world, its seas visible from Earth through the transparent nitrogen atmosphere. But like Titan and Europa before it, Triton's low gravity would prove insufficient to retain these volatiles indefinitely. Over millions of years, the atmosphere would escape to space, the ocean would freeze, and then sublime away. Triton would become a smaller, drier remnant of its former self, another example of the tragedy that befalls outer solar system moons transplanted to warmer orbits, where their frozen volatiles cannot remain stable. Phobos and Deimos, the miniature moons. Mars, our planetary neighbor, possesses two small moons that barely qualify for the title. Phobos and Deimos, named after the Greek gods of fear and panic who accompanied their father Ares into battle, are tiny irregular bodies that more closely resemble captured asteroids than traditional moons. Phobos, the larger of the pair, spans a mere 27 kilometers at its widest point, while Deimos extends only 15 kilometers across. These are not spherical worlds, their gravity insufficient to pull them into round shapes. Instead, they are misshapen lumps of rock and dust, pockmarked with craters and coated in charcoal-hued regolith. The dimensions of these moonlets are so modest that calling them moons seems almost generous. They are more than 100 times smaller than Earth's moon by linear dimension, and their mass deficit is even more extreme, since mass scales with the cube of linear dimension. If we swapped our substantial moon for the diminutive Phobos and Deimos, the night sky would transform dramatically, but not in a pleasant way. The familiar lunar disk, so prominent and bright that it illuminates the landscape and casts distinct shadows, would vanish entirely. In its place would appear two objects barely distinguishable from bright stars. With a telescope or binoculars, an observer could resolve Phobos and Deimos as tiny disks rather than point sources, and their motion against the background stars would be noticeable. but to the naked eye, they would appear as nothing more than unusually bright stars, or perhaps artificial satellites. Picking them out from the constellations would require careful observation and prior knowledge of where to look. The consequences of losing the moon's light would extend far beyond aesthetics. Moonlight, though a mere reflection of sunlight and thousands of times dimmer, plays a crucial role in terrestrial ecosystems. Nocturnal animals have evolved over millions of years to navigate, hunt, and avoid predators using moonlight as their primary illumination source. Owls rely on moonlight to spot prey moving through grass and underbrush. Moths and other nocturnal insects time their activities to lunar phases. Marine creatures use moonlight penetrating ocean waters to orient themselves and coordinate behaviors. With moonlight effectively eliminated, these species would face profound challenges. Nocturnal hunting would become far more difficult. Predator-prey relationships would shift as the playing field changed. Migration patterns keyed to lunar phases would be disrupted. The ecological consequences would ripple through food webs, potentially leading to population crashes or explosions as species struggled to adapt to the new darkness. Some species might shift toward more crepuscular activity patterns, concentrating their activity in twilight hours when some natural light remains available. Others might evolve enhanced sensitivity to starlight or greater reliance on non-visual senses. Astronomers would celebrate the darker skies. Light pollution remains a constant challenge for astronomical observation, limiting what can be seen from Earth's surface. Eliminating moonlight would partially offset terrestrial light pollution, allowing observation of fainter objects. Deep sky objects like distant galaxies and nebulae would become more visible. The Milky Way would be more prominent even from light-polluted urban areas. But for the rest of humanity, the loss of moonlight would diminish the aesthetic and practical benefits that moonlit nights have provided throughout our evolution. The gravitational consequences would be equally severe. Phobos and Deimos combined possess less than 1/100% of our moon's mass. Their gravitational influence on Earth would be negligible. Oceanic tides, currently driven primarily by the moon with a smaller solar component, would be reduced to purely solar tides. Tidal ranges would drop dramatically, potentially by as much as 75%. Coastal ecosystems finely tuned to current tidal patterns would face catastrophic disruption. Marine life would be among the hardest hit. Species that spawn in intertidal zones, relying on tides to bring them into shallow waters where eggs and larvae can develop, would lose this crucial habitat. Fish that time their migrations to tidal currents would find those currents greatly weakened or absent. Tidal marshes, among the most productive ecosystems on Earth and crucial nurseries for countless marine species, would be transformed as the regular inundation cycle that defines them disappeared. The loss of strong tides would affect ocean circulation patterns. Tidal mixing plays an important role in ocean dynamics, particularly in coastal waters, where it helps distribute nutrients, oxygen, and heat. Reduced tidal mixing could lead to more stratified coastal waters, potentially creating oxygen-depleted zones where marine life struggles to survive. The long-term impacts on fisheries and marine biodiversity would likely be severe. Wind patterns would shift as well. Tides don't just affect water, they affect the atmosphere too, creating subtle pressure variations that influence wind patterns. Weather prediction models would need to be recalibrated for a world without significant lunar tides. Climate regulation mechanisms that depend partly on ocean-atmosphere interactions driven by tidal mixing would be altered in ways difficult to predict. But the most severe consequences would emerge over geological timescales. Our moon provides crucial stabilization to Earth's axial tilt. Without this substantial gravitational anchor, Earth's axis would begin to wobble chaotically over millions of years. The tilt could vary from nearly 0 degrees, where the equator aligns with the orbital plane and seasons almost disappear, to 60 degrees or more, where polar regions would experience months of continuous daylight followed by months of continuous darkness, while the equator would see the sun traverse extreme arcs across the sky. These axial variations would produce climate swings of staggering magnitude. In a low-tilt configuration, temperature differences between equator and poles would decrease, potentially melting polar ice caps and redistributing moisture in the atmosphere. In a high-tilt configuration, seasonal extremes would intensify dramatically, with summers hot enough to boil water in polar regions and winters cold enough to freeze oceans at temperate latitudes. Ice ages would become more frequent and severe. The stable climate that allowed complex life to evolve and civilizations to develop would be replaced by constantly shifting conditions that would challenge the adaptability of most species. Earth has enjoyed a relatively stable axial tilt for hundreds of millions of years, held steady by the moon's gravitational influence. Venus, lacking a large moon, sees its axial tilt vary chaotically over millions of years. Mars, with only its tiny moons Phobos and Deimos, has an axial tilt that varies between approximately 15 and 35 degrees over periods of millions of years, producing extreme climate swings. Earth would follow a similar pattern, wobbling wildly without the moon's stabilizing presence. Phobos itself presents an additional long-term danger. This tiny moon is gradually spiraling inward toward Mars, approaching the planet by approximately 2 meters every century. In roughly 50 million years, Phobos will either break apart, torn asunder by tidal forces as it crosses inside Mars's Roche limit, or it will impact the planet directly. If Phobos became Earth's moon and retained this inward spiral, humanity would face the prospect of a 27-kilometer asteroid plowing into the planet in slow motion over tens of millions of years. Such an impact would likely exceed the Chicxulub impact that ended the Cretaceous period and wiped out the non-avian dinosaurs. That impactor was estimated at roughly 10 to 15 kilometers in diameter, and it created a global catastrophe that extinguished approximately 75% of all species on Earth. Phobos, being perhaps twice as large, would deliver even more kinetic energy. The impact would vaporize portions of Earth's crust, eject debris into orbit that would subsequently rain back down as molten droplets, ignite global wildfires, and potentially push Earth's climate past a tipping point that would render the planet uninhabitable for most complex life. When viewed in totality, swapping our moon for Phobos and Deimos represents perhaps the worst scenario in this entire thought experiment. The benefits of darker skies and reduced coastal erosion would be utterly overwhelmed by ecological catastrophe, climate chaos, and the ultimate threat of extinction-level impact. Our current moon, for all its familiar ordinariness, provides services to Earth that are difficult to appreciate until contemplating life without them. Enceladus, the reflective snowball. Saturn's moon Enceladus occupies a special place in planetary science, representing one of the most intriguing targets in the search for extraterrestrial life. This small, icy world, dwarfed by most major moons, nonetheless harbors mysteries that have captivated scientists since the Cassini spacecraft revealed its secrets in the early 21st century. Enceladus is not merely a passive ball of ice orbiting Saturn. Instead, it actively contributes to the planet's ring system, spraying plumes of water ice and organic compounds from cracks in its south polar region. These cryovolcanic plumes, driven by internal heat and subsurface ocean pressure, blast material hundreds of kilometers into space. Some of this material falls back to Enceladus's surface, coating it in fresh snow and making it the most reflective surface in the entire solar system. Other material escapes Enceladus entirely, going into orbit around Saturn, where it becomes part of the tenuous outer E-ring. In essence, Enceladus is building a piece of Saturn's ring system in real time, a process that has likely continued for millions of years. If we swapped our moon for Enceladus, the visual impact would be noticeable, but not overwhelming. Enceladus's brilliant white surface would reflect sunlight with extraordinary efficiency, creating a bright presence in the night sky, despite the moon's relatively small size. Nights would be dimmer than with our current moon, but nowhere near as dark as with Mars's miniature satellites. The moon would appear smaller, its reduced apparent size partially offset by its high reflectivity. The gravitational consequences would unfortunately mirror those encountered with Phobos and Deimos. Enceladus, despite being more substantial than the Martian moons, still possesses far less mass than Earth's moon. The tidal forces it would generate would be dramatically weaker than those we currently experience. Oceanic tides would drop sharply, becoming primarily solar-driven rather than lunar-driven. All the ecological disruptions described for Phobos and Deimos would apply here as well. Disrupted coastal ecosystems, altered ocean circulation, affected marine life populations. The long-term axial stability issue would similarly rear its head. Without a substantial moon to anchor Earth's axial tilt, our planet's orientation would drift over millions of years, producing the same climate chaos that would result from replacing the moon with Phobos and Deimos. Ice ages would intensify and become more frequent. Climate zones would shift unpredictably. The stable conditions that allowed human civilization to develop would give way to fluctuating environments that would challenge agricultural systems and force populations to constantly adapt to changing conditions. Yet in the short term, Enceladus would provide one benefit that Mars's moons cannot: sufficient brightness to maintain at least some functionality for nocturnal species and human activities. While not as bright as our current moon, Enceladus would provide enough illumination for navigation and for creatures that rely on moonlight. The complete darkness that would result from Phobos and Deimos would be avoided, reducing, though not eliminating, the ecological disruption. Enceladus itself would undergo rapid transformation once exposed to the solar radiation intensity of Earth's orbit. Saturn orbits roughly 9.5 times farther from the Sun than Earth does, meaning that solar radiation at Saturn's distance is nearly 100 times weaker than at Earth's orbit. Enceladus has existed in this dim, cold environment throughout its history, maintaining surface temperatures around -200 degrees Celsius. Its ice shell remains solid and stable, though internal tidal heating from Saturn keeps subsurface regions warm enough for liquid water to exist. Transplanted to Earth's orbit, Enceladus would be flooded with solar energy approximately 100 times more intense than anything it has experienced. The immediate consequence would be accelerated sublimation of surface ice. The pristine snow coating that makes Enceladus so reflective would begin to vaporize, creating a thin atmosphere of water vapor. As warming continued, deeper ice layers would sublimate as well. Enceladus's ice shell is significantly thinner than those of giants like Europa or Ganymede, perhaps only a few tens of kilometers thick rather than hundreds of kilometers. This relatively thin ice shell means that the subsurface ocean would be revealed relatively quickly, geologically speaking. Enceladus harbors a global subsurface ocean beneath its ice crust, confirmed by multiple lines of evidence, including libration measurements, gravity data, and the composition of the plumes it ejects. As the ice melted away, this ocean would be exposed to direct observation for the first time. Enceladus would transition from an ice moon to a water moon, its surface dominated by seas rather than frozen crust. The astrobiological implications would be profound. The plumes that Enceladus ejects contain not just water ice, but also organic compounds, carbon-bearing molecules that are the building blocks of life as we understand it. The subsurface ocean from which these plumes originate has been in contact with Enceladus's rocky core, allowing chemical reactions between water and rock that could provide chemical energy for life. On Earth, hydrothermal vents on the ocean floor support ecosystems based on chemosynthesis rather than photosynthesis, deriving energy from chemical reactions rather than sunlight. If similar ecosystems exist in Enceladus's ocean, exposing that ocean in Earth orbit would allow direct sampling and study. Submarines could be deployed into alien seas. Samples could be returned to Earth for detailed analysis. If life is found, even simple microbial life, it would revolutionize our understanding of biology and our place in the universe. The discovery would confirm that life can arise independently in different environments, suggesting that the universe may be filled with living worlds rather than Earth being a unique oasis in a sterile cosmos. But as with every other outer solar system moon we've considered, Enceladus's transformation would be temporary. Its low gravity, adequate to retain water vapor in the cold outer solar system, would prove insufficient in the warm inner solar system. Over millions of years, the newly revealed ocean would gradually escape to space. Solar radiation would break water molecules into hydrogen and oxygen. The light hydrogen would escape entirely, while oxygen might react with surface materials or accumulate as a thin atmosphere before eventually being stripped away by solar wind. The cryovolcanic plumes that currently make Enceladus so fascinating would cease shortly after the swap. These plumes are driven by tidal heating from Saturn and by pressure from the subsurface ocean. Removed from Saturn's gravitational influence, the tidal heating would stop. As the ice melted and the ocean was exposed, the pressure that drives the plumes through cracks in the ice shell would be released. Enceladus would become geologically quiet, its dramatic geysers silenced. In time, Enceladus would become a small, airless world, its water lost to space, and its surface, perhaps bearing only frozen remnants to suggest the ocean that once covered it. The brilliant white snowball would become just another gray, crater-marked moon, indistinguishable from countless other small bodies throughout the solar system. But, for a brief period, humanity would have the opportunity to study an alien ocean up close, to search for signs of life in waters that have been sealed off from Earth's biosphere since the solar system formed. That window of opportunity, though temporary, would be scientifically invaluable. This cosmic thought experiment reveals the unique value of our moon. Not too large, not too small, not too close, not too far, it occupies a Goldilocks zone of lunar characteristics that provides substantial benefits while avoiding catastrophic consequences. The moon stabilizes Earth's axial tilt, providing climate stability that has allowed complex ecosystems to evolve and human civilization to flourish. It generates tides that drive coastal ecosystems and ocean mixing without flooding continents. It provides sufficient light to illuminate nights without overwhelming the darkness that nocturnal species require. Swapping our moon for other solar system moons would produce outcomes ranging from fascinating but manageable to utterly catastrophic. The largest moons would unleash tidal forces that would literally reshape coastlines and trigger earthquakes. The smallest would leave Earth spinning through space with inadequate gravitational anchoring, leading to climate chaos over geological time. Even intermediate-sized moons would alter Earth's environment in ways that would challenge life's adaptability. Yet these scenarios also highlight the extraordinary diversity of moons throughout the solar system. From volcanic hellscapes to ice-crusted oceans, from moons with their own magnetic fields to captured asteroids barely large enough to qualify as satellites, our solar system's collection of natural satellites represents a range of environments and processes that continue to surprise and fascinate scientists. Each moon tells a story about the conditions in which it formed, the environment it has experienced, and the processes that have shaped it over billions of years. The exploration of these moons represents one of humanity's great scientific frontiers. Space missions to Europa, Enceladus, Titan, and other moons promise discoveries that could reshape our understanding of how common life might be in the universe. Finding evidence of life, even simple microbial life on another moon, would confirm that biology is not unique to Earth, suggesting that living worlds might be common throughout the cosmos. Even if no life is found, studying these diverse environments provides crucial data for understanding planetary formation, the distribution of water and organic compounds in the solar system, and the range of conditions under which habitable environments can exist. For now, we can appreciate our moon for what it is, a constant companion that has orbited Earth for over 4 billion years, shaping tides, stabilizing climate, inspiring countless cultures, and recently serving as humanity's first destination beyond our home world. The familiar gray sphere that rises each night may lack the dramatic features of volcanic Io, the mysterious oceans of Europa and Enceladus, or the thick atmosphere of Titan. But it provides precisely what Earth needs: a reliable gravitational anchor, moderate tides, sufficient but not overwhelming light, and a nearby destination where humanity has already planted footprints and where future generations will surely return. The moon remains the closest celestial body, reachable in 3 days by spacecraft, and potentially the site of future human settlements. It offers resources, including water ice at its poles, rare earth elements in its crust, and a stable platform for astronomical observations unhindered by Earth's atmosphere. Perhaps most importantly, it represents a testing ground where humanity can learn to live and work in space before venturing to more distant and challenging destinations. Whatever wonders await us on the moons of Jupiter and Saturn, our own moon will likely serve as the gateway that allows us to reach them.